So as you said, I'm Dave Thompson. I'm a recent Texas State transplant, and I'm going to talk today about some prior work and the directions we're thinking about heading. The topic is embedded systems for longitudinal sleep monitoring. So first question is, who am I or what's going on? I was born in Kansas. I grew up on a farm in Kansas, then escaped to a few different places for undergraduate and spent a year in Japan on a Fulbright, had some relative academic success for a little while. Showed up at the University of Michigan, where I did my graduate work. And then after finishing up my PhD in biomedical engineering, I did a postdoc, had the simple joy of working with Cindy Chestek, who's among the best humans I've ever known. So we did a lot of things, but I got to work with monkeys, brain implants, genetically engineered viruses, lasers, and video games. And I figured, like, if I just managed to put one of those monkeys into space, I would have just been done, just retired, right? Like, that's everything a nerd could ever want to do all in one little year and a half postdoc. Then I went to K-State, went back to Kansas, where I was a tenured associate professor, and among other things, directed a COBRE Center, which is an idea state mechanism center of biomedical research excellence, and was trying to help early stage faculty success in psychological sciences. So you might ask, how is an engineer doing stuff in psych sciences? And it was a weird series of events that we don't need to go back into. But yeah, I did that for 2 years. And then I signed away $2.7 million in annual research expenditures to come down to Texas State. So I'm here right now, and I've been here since August, and it's a change, but it's been lovely. It's been lovely, and everyone's been lovely, so I appreciate this opportunity. So another quick note is that this is my email address. I have sort of a one-man vendetta against Outlook, and I really promise I've never deliberately not seen an email, but I have dropped a lot of emails. I can't find them, even when I search for them, even when I remember who sent them, even when I remember the subject title and the date it was sent. I can't find the darn thing. So if you send me an email and I don't respond within 24 hours, then email again. Okay. And I will see it that time and I will help you. But in the interim, you know, there's many Dave Thompsons. As it turns out, there's only one me. And that's the one to get a hold of me. And do not, if you want to talk about something, feel free to just pepper that. And eventually I will see that and it will come through. Okay. I wanted to start today by talking about a couple of long-term collaborators that I've worked with and that were a huge part of the success of this project that we're going to cover today, and that I imagine continuing to work with going forward. So these are some guys that were important to our success. Steve Warren got me interested in sleep monitoring at all. He wrote the grant that we're going to discuss today. Charles Carlson was a graduate student and then eventually became a teaching professor at the university and was very, very involved. A lot of his graduate work, his dissertation was on this project. And then Carl Audi joined later. He's from kinesiology rather than engineering, and he was just a true treasure to work with. I love interdisciplinary collaborations. He had eventually a PhD student who would go on and take a bunch of data for us, and she was a true treasure and somehow happy with middle authorship. So that was the thing that she wanted to do. She wanted to do all this work and collect data for us. And if you've ever worked with human subjects collection, it is a tremendous time suck just to go in and do all of that. And Vanessa Rose Turpin, fine human to work with. And Carl was her mentor and good friend as well. So the first question that I want to address is, why do I care about sleep monitoring? Right? What is it about this that matters to us? And the short answer is, you know, in academia, we do a lot of research, but it's really me search, right? It's the things that are close to us, the things that are close to home. And so, among other things, I've made very questionable life decisions. I have 4 children and recently also acquired these things, which are kittens, if you can't tell, and they sleep like I want to sleep, right? Everywhere, splayed out, completely blissful to the world. And that's not how I sleep, because I have kittens in the house, and they instead are busy destroying all sorts of things. And I wake up, I sleep like this now, where like, what is that noise? What is happening? Why is why is that power cord, sorry, Texas State, that Apple power cord that the kittens kind of ate. Anyway, so, you know, why are there holes in this now? So Okay, that's a joke, and it's used to show pictures. This is what that is, but okay, but in all seriousness, why do you study sleep? You study sleep, and it feels sort of silly to stress this, but it affects everything. It affects everything. If you go on to Google Scholar or your favorite engine and you start looking and saying sleep correlates with blank, yes, it does, right? It does. It's correlated with weight loss, persistent weight loss or weight gain is correlated with poor sleep for the gain. I know about that one. You have cardiac health, you have cognitive health, you have just everything of interest is correlated to sleep loss. Now, what we're going to focus on today is some technology that we use and develop to work with a unique population. That population is children with autism. So this is kind of an interesting take. This was Steve Warren's idea. We all came together as co-PI on this grant, and we were looking, and we had a conversation with a clinical partner, a potential clinical partner in Wichita, Kansas, by the name of HeartSpring. HeartSpring is a de facto autism clinic. It's not actually an autism clinic. They take all etiologies, but what they require is that the person be a minor and in need of 24-hour care. If you look at the prevalence numbers, then it's an autism clinic, right? And 96% of their patients at any given point in time, which roughly means 1 or 2 non-autism primary diagnoses, but mostly primary autism diagnosis. These are people who have exhausted their family support resources, right? This is, if you look at you have to be careful when talking about autism. There's a good chance people in this room who are productive or might be autistic and might have very meaningful lives, right? But when you look at the lower functioning end, the nonverbal end, it's a tremendous burden for the families that provide care to these children. Right? And so eventually, some of them will exhaust that family care structure and wind up in a facility like this, where they can receive, meaningful educational opportunities. They can learn to improve their behavior. They have lots of things going on there for that care. Now, but if you're familiar with folks with autism, there are challenges with trying to get objective measures of what's going on in their lives, right? So, among other things, our clinical collaborator says that we don't really understand how these children sleep. Some of them don't appear to sleep. If you look at them throughout the night, it's not clear that they're ever doing what those kittens did in the earlier slide, right? They're moving around, they're doing all sorts of activities throughout the night. And they're wired different. They've got different things going on. So this director wanted to get at this population and kind of understand what that nighttime behavior looked like. And okay, so this is the grant that we won and it was completed a few years ago on research to quantify the health and development of children with disabilities around the clock, with the goal of mostly the nighttime sleep monitoring. And I'm going to talk today about ballistic cardiogram and the hardware and software packages we developed for part of that project. But of course, there's a disclaimer. This was NSF funded, but it doesn't mean that the NSF did all of this or that the opinions or findings here are from the NSF. Okay, so these are some publicly available images of children with some severe disabilities. And when you go to work with some of these folks, right, some of these folks can't have seams on the inside of their clothing, right? So you can't think about it in terms of a normal biomedical engineering approach. We're going to throw some sensors on these people. We're going to call it a day, right? That's not going to work in this environment. So the question then is how can we monitor? How can we get objective measures out? And I'm going to do this slightly out of order. There are people in this room that have done a lot of polysomnography. This is the gold standard sleep monitoring system. If you have trouble sleeping and you go to a sleep lab, this is what they would wire you up with, right? So you've got EEG electrodes, electroencephalogram, you've got EOG electrodes, that's the ocular muscles around the eye to detect eye movements. You've got electromyograms maybe on the chin for chewing and teeth grinding and different things. You've got sensors everywhere, including electrocardiogram for detecting heartbeats and heart abnormalities, and maybe some stuff for airflow if you've got apnea events. This is not replicable in our population, but this is the sort of thing that people expect to see for studying sleep. So here's a little figure with some of these sensors present. And then this is what we call a hypnogram, which describes the cycle through which a person moves throughout the night. Typically in a neurotypical individual with a typical sleep pattern and no children, because there's no night waking during most of this. But then you see like lots of stage N3, sort of deep sleep earlier in the night, transitioning into more REM. This would be nuts. If I ever had a sleep hypnogram that looked like this, I'd be happy, at least for 5 minutes. But there's some problems with this, and just I feel like I'm belaboring the point a bit, but you can't do sensors like this in this population. That is not possible. It's not remotely potentially possible, right? Yeah, just there we go. So we can't do this. And moreover, I would argue you can't do this longitudinally, even in a healthy population. It's not feasible to set up a system like this every night and take data and try to see how patterns of sleep change or how long-term behaviors are there. Instead, polysomnography, the typical gold standard, I would argue, is a snapshot. It's one picture of a person's sleep health, and it cannot be anything more than that. So the world has come up with a solution that they think works, and that solution is wearables, right? There's probably people in this room that monitor their sleep with wearable smartwatch or similar device, and you can get some idea of how you slept that night. I'll show you a couple of pictures just in case you're not familiar. This slide's a little bit old, so the version numbers have changed, but the players are still more or less the same. You've got Apple Watches, you've got Fitbits, you've got Garmin's, you've got some bio harnesses, if you like that direction. Lots of different wearable devices, which are commercially available. Some of them have to use pulse oximetry or photoplethysmograms. So what that word is, the picture of a light-based picture of circulation, which is achieved with a couple of different diodes. One of my second undergraduate research project was designing a pulse oximeter based on reflectance. I think the previous version of Apple Watches maybe had a pulse ox on it. This is one non-invasive measure of cardiac activity. Let's say this, you'll see this picture again here in a second. So this will be relevant to us, but this is one non-invasive picture. And then when they're done, you'll see something that looks like this. You'll see a picture and you'll have deep sleep, activity or waking, and you get some idea of what in some store typically that's all proprietary and you don't know how it's generated, but you wake up and you say, oh, I slept well. My wife is addicted to her sleep tracker. I love my wife very much, but sometimes she wakes up and she looks at that and do you not know, right? Do you not know how you slept, right? Like this is very strange to me, but she gets a great deal of joy from interacting with her sleep tracker every day, and more power to it. So, but why are wearables not suitable in this environment? Well, they're not suitable because they still require compliance, right? You still have to put the thing on. My wife sometimes has to charge her sleep tracker, so she puts it to the side. So we missed that night. Why? And in this population, well, in any population, I would argue that compliance is tough. People don't comply with medications. People don't comply with usage, right? So it's hard anywhere. It's extremely challenging in addition for older adults, which is something we'll touch on later in the talk. But it's a lot of older adults don't want to wear something that is there to say that there might be a problem. Like that's not a desirable outcome to them, to wear something, to interact with this on a daily basis. And it just doesn't work in this population. You can't get them to wear something. You do well. I have a kind of dark sense of humor, but you do well to get them not to eat it, right? Or to tear it apart or shred it, right? It's just not possible. So there are a couple of other alternatives that I'm going to gloss over. You could use cameras. I don't like cameras from a privacy perspective. I just feel like even if we don't save the images, we're going to save the images to do analysis, just like the TSA saved in the pictures of you, right? When they said they wouldn't. So like you're going to save the pictures, and once they're saved on a hard drive, they're available to be problems down the line. I don't like that. So that's a privacy perspective issue. And then there's Wi-Fi or radar-based technologies, which work really nice in conference papers, but I happen to think don't work in If you talk to the people who do the Wi-Fi sensing research, if you sort of turn sideways, suddenly it's all off. You can't measure heart rate reliably with these devices. You can if the person sits and stands there right there, and it's wonderful, but it's kind of academically interesting. So where do I think we go with this? I think we go with systems that are embedded in furniture. It's a bit of a jump. It's a bit of a jump to get there. We're not putting the sensor on the person, we're putting the sensor on furniture in the room, and furniture that they're going to choose to interact with of their free will. It's beds, in older adults, it's chairs, right? What are you going to sleep on? You're going to sleep on your bed, right? So if you put the sensors on the bed, now if they don't lay on the bed, we're not going to get data that day, right? That's still, there is still a compliance piece. But the nice part is it's aligned with the incentives that they're already interacting. They want to sleep, they're going to sleep there. That's the comfy spot to sleep, right? So we'll put the sensors there. And if we can get them sufficiently unobtrusive, then, we can get recordings from an otherwise challenging population. Now, there are furniture-based systems on the market as well. These two are here. I happen to know of these two because these are two commercial. We use the sensor that is used in both of these systems. So these two are clients of the same company that we bought some of our sensors from. But this is the embedded system. On the right is the ENFit QS, which are under mattress, or at least under sheet and potentially under mattress sensors for measuring stuff. So these are commercial products. We did not choose to use them because we couldn't get access to the data that was necessary. Instead, we built this bed, which has a bunch of different sensors in it. We've got load cells. Load cells are a pressure sensor that shows up in the corners of the bed. You can put it under the frame if you like. You can put it depending on the construction of the bed. Casters are not my friend. I have many bad nightmares about beds with casters on them. But if they have legs and we can put them under the legs of the bed, we can build coasters and different things that help to transfer that force. We have under mattress sensors, which are films very similar to the bedded system. And then for this particular one for heart spring, we had an enuresis system based on thermocouples. You wouldn't do that in other populations, but this is a population that had some trouble with bedwetting, right? So they wanted to know that. Some of these children had disturbed sleep, not necessarily because of their diagnosis, but because legally they had to check the bed every 2 hours to see if there had been an enuresis event. And so that was a continual disturbance to their sleep pattern, right? So one of the goals of this project was to detect that event so that the sheets could be changed and things could be improved in shorter order than every 2 hours. Okay, so the thermocouples are just a temperature sensor, and we just detect the event based on a pattern from there. But it's not the focus of today, and I don't intend to continue with that sense. We get lots of interesting data from this. I've got a separate slide on it, but first I've got a couple pictures of it in use. We use it in open houses and as well as in research. It was a pretty interesting recruitment tool for subjects. And we ran a bunch of stuff over in the Longitudinal Medical Center, which is on Bay State's campus. Carl Lottie's group, again, did a bunch of that data collection. But this is my first graduate student here on this lineup. And there's Charles Carlson that we did. Okay, what do we get? We've talked a lot about the technology. What can I provide? Mostly I get cardiac data through a thing called ballistocardiogram. We'll define that here shortly, but it's a signature of heartbeats. So I get heartbeat timers. So I have heart rate, I have heart rate variability. Those are things of interest in the physiological health world. I also get respiration. As you breathe in, right, you gain mass because you have additional mass inside of your lungs. And I can see that. It's crystal clear in the data. You'll see it with naked eye when I show you the data here in a second. I can also get activity or movement because we are force sensors and we can detect movement. It unfortunately swamps out the respiration and the heart rate, but I can get whether you're moving or not. And then I can do center of pressure. So center of pressure is useful for a few things, but I've got multiple sensors. So whichever one you're the closest to is where you've got most of your weight. And so I can back calculate where you are in the bed, at least if you're a point and not a person, you're a person, but we can figure out where the center of it is. And that's of value because you can watch that trajectory and you can see certain activities. You can see people rolling over. You can see them getting closer to the edge of the bed. You can start thinking about things like bed exit prediction versus bed exit protection. And then we've gone on to show a lot of things. So some of these have wound up in publications, and one of them is a provisional patent. So we've shown that the signals carry information about the body and the platform that it's on. We've been able to do some sleep staging. We've been able to detect and estimate blood pressure and how it changes as people hold their breath. And then the provisional patents on body composition. It turns out the BCG looks a little different based on the tissue that it travels through. So we've been able to do. It's sort of fun. It's like the first new technology for body composition in kind of a while. So it's been bioimpedance and calipers and immersion for quite a while. So we got a provisional patent on that. So that was fun. Okay, so what can we do with it? We've got the sensor. What does it look like? It looks like this. You've got a bunch of forces, and those forces are changing over time. You can actually see this on the weigh scale. If you just stand on the bathroom scale, these forces are on the order of half a pound to a pound to 2 pounds, depending on your physiology. What are those forces? It's your blood is ejected from the ventricle as your heart beats. Then it goes through a series of accelerations as it travels through your vasculature. Right? So it has to go from here to there. That's changing velocity. That's acceleration. That's forces. We measure those forces. We can see when the heart beats. This is a rough signal from a stoke, and you can kind of see that they're relatively common peaks, and you also see this general trend of up and down. The up and down is respiration. That's an easy one. I promise you see that. And then, you're breathing about every 5-6 heartbeats in this particular figure. And this is a close-up of a couple of signals you might be familiar with. So the blue is electrocardiogram. If you've ever gone in for a heart test, you've seen this one. The blue is electrocardiogram. I'm going to go to a zoom in. It's bothering me. And what you see, this is the electrical contracture event of the ventricle. So that's the heartbeat, if you will. And then a little while later, the red is photoplethysmogram and pulse oximeter, measuring, roughly speaking, the amount of blood in a peripheral vessel. That spikes up a little bit after the contractural event, and the green is our BCG or ballistocardiogram. You can see it's just right around the time when the blood's actually moving. So it's a little bit of a delay between the contracture event, between the electrical event which causes the contracture and the blood actually moves. It takes some time for that muscle to respond. All right, but you can see it's reasonably persistent. You can see these large peaks right around the time of each of those electrical events. Here's a slide showing that we can separate out the respiration artifact from the ballistocardiogram, get an active measurement of the ballistocardiogram, right? So taking out that sort of regular respiratory artifact. And then here, we were looking at peak detection algorithms. It is somewhat frustrating. There are lots of different peak-like activities there. You want to find the biggest one. You would think it's 2026. There would be an established winner and a good way to find the big peaks out of a series of time data. There aren't. There's lots of competing ways, all of which have led to a publication and then a group that moved on to other topics and did not think about it ever again. And all of them claim to be better than all the other ones. We had to do a comparison study to figure out which one won. But lucky Mr. Bruiser won that comparison, and so we use Bruiser's method now. But this was a question that occupied a fair bit of our time. How do you find the heartbeats out of this relatively peaky signal? And then, given that, so now we have heart rate, we have respiration, we have movement, we have all these things. What can we do? Well, because we were in a care facility and we had the ability to track various behaviors already, they were tracking all of these behaviors, and they had this kind of fancy system where the pair would just touch a couple of fingers together to record one of these events. So we had self-injurious behavior, property destruction, tantrums, these sorts of things. Said, okay, can we guess, based on sleep, whether these events are more or less likely to occur? We've got the gold standard of that. And it's worth mentioning that getting this data is challenging because the parents are difficult to consent. They're difficult to reach for consent in these facilities because, unfortunately, very understandable. They have gone through some real stuff in their life that we're fortunate not to have gone through ourselves, and then they made a difficult decision to commit the child to a full-time care facility. They don't want to answer the phone, and we can't blame, right? We can't divorce, we can't do whatever. It's really hard to get that consent. We only got 2 people to consent to having a child hooked up
for this system. That said, they consented for as long as we wanted to. So we had 300 some odd nights of data from one of these kids. We have better than 100 nights of data, and you can start to do some real science on the small n, but the big N of days. And what we found is that sure enough, it's not the previous night's sleep, it's mostly 2 nights prior and a little bit of information from additional nights. This was my contribution, in addition to some of the hardware developments, my contribution to the project based on my own history as a student. I'm not proud of it, but I pulled a bunch of all-nighters. And in general, the next day I was sort of okay. And the following day I was completely useless, right? So that was my own observation in my own life. And I said, maybe consider several nights, not just one night. And sure enough, the correlation is strongest 2 nights prior. That's the night that's the most important. But we were able to guess with some degree of accuracy using a couple of different classifiers whether the day was going to be good or bad. I could show you, I've got a slide later if we want to pull it up. There's a pretty clear correlation between the night's sleep and the next and the behavior, and it's obviously offset. It's offset by relative. So the main thing we looked at in these children in particular was a measure of actigraphy, or measure just total time that we saw movement artifacts, and that was the most strongly correlated rather than basing on heart rate and sleep staging. Roughly speaking, if they stayed still, they were doing better a couple days down the road. They moved around a lot. Now, from a nursing perspective, we're trying to see what to do with that. Defer to my folks in psychology whether you really want to tell the nurses to expect bad behavior that day. There's questions about how that's going to impact behavior, but I think as a parent, for example, I might want to know what I'm getting into on the day. Or think about. Well, yeah, I have kids. Sometimes it's helpful to know that they didn't sleep well and that that's what day is going to go in such a way that it would be good to prepare yourself.